Welcome. This video is going to look at the rest of section 1.2 from the Brown SL IB chemistry book. And in section 1.2, the last half talks about empirical formulas. An empirical formula is defined as the simplest whole number ratio of the elements in a compound. Now, for an ionic compound, the formula unit will be the empirical formula because, by definition, the formula unit is the fewest number of positive and negative ions needed for the electron transfer to occur. But covalent compounds don't always have empirical formulas, or the molecular formula isn't always the same as the empirical formula, I should say. So, for example, CO2, carbon dioxide, that is the simplest formula, 1 to 2 carbon to oxygen. But if I had a sugar with the formula C6H12O6, that simplest formula would be CH2O. So that's what we mean by an empirical formula. And to determine an empirical formula, you need to have experimental data that lets you know the mass of each element that's part of that compound. And then we convert the mass to moles and come up with the ratio. So the steps I like to use in determining an empirical formula is to find the mass of each element in the compound. And again, you have to do this experimentally or it's given to you in a word problem. Then you convert each mass to moles using the appropriate molar mass. And then step 3, I like to write the compound's formula using these molar amounts to remind me that that's what subscripts really are, is the molar amounts or the molar ratios. And then I divide all the subscripts by the smallest subscript. And if they all round to whole numbers when I take into account my sig figs, then I'm done. But if I end up with a decimal that really represents a fraction, like 0.25 is 1/4, or 0.33 is 1/3, 0.50 1/2, 0.67 2/3, 0.75 3/4, those are kind of the common ones you might run into. Then I need to multiply all the subscripts by the denominator to change those into whole numbers. And it simply means if you had something like N2O3, the simplest ratio where we have a 1 would be N1O1.5, but we don't keep the 0.5, so then that translates to N2O3. So sometimes you will see those fractions. No big deal. So in my example here, I'm just going to make a quick correction here. This is really supposed to be 1.121 grams of nitrogen. So to find the empirical formula, I'm first going to write down what I know. I know I have 1.121 grams of nitrogen. I have 0.161 grams of hydrogen. I have 0.480 grams of oxygen. And I have 0.640 grams of oxygen. So I need to change each one to moles by dividing by the molar mass, which I just get from the periodic table. So when I start there with nitrogen, I'm going to go ahead and pause and go ahead and get all my molar amounts. And you maybe want to try that on your own as well. So if you look at what I've done here, I came up with 0.0800 moles of nitrogen when I round off to sig figs, 0.1594 moles of hydrogen. Rounding off, I have just 0.0400 moles of carbon and 0.0400 moles of oxygen. So I've rewritten my formula, my molecular formula here, using NHCNO and then these funny subscripts, and I'm dividing by 0.040 because that's my simplest ratio. And I'm going to come up with N2, and then the 0.1594, even when I divide by 0.04, that's 3.985. That's definitely within sig figs of H4, and then C and O are going to be 1 each. So I can assume that this is my empirical formula. So here's one for you to try, where you have the mineral celestine, consists mostly of strontium, sulfur, and oxygen. It's found by combustion analysis, which we'll talk about a little bit more, but basically it means it's been burnt. And it's 47.7% by mass strontium, 17.46% by mass sulfur, and the remainder is oxygen. So a couple things to get you started here is, first of all, when you see percents, just think grams. That's really 100 gram sample. So I have 47.70 grams of strontium that I'm going to change to moles. I have 17.46 grams of sulfur that I need to change to moles. So I need to look up some molar masses. And then oxygen, if the remainder is oxygen, I can just take my 47.7 plus my 17.46. That's 65.16. And if I subtract that from 100, then the other 34.84%, or 34.84 grams, has to be oxygen. So go ahead and see if you can come up with an empirical formula for this before you watch the rest of my solution. So if you follow my solution here, I found strontium has a molar mass of 87.62, so I have 0.5444 moles of strontium. Sulfur also works out to be 0.5444 moles. Oxygen, I come up with 2.1775. Now, just a thing about sig figs, if you can keep these numbers in your calculator and not have to round to your final answer, that's really the best, because the more you round, the more air you introduce. And eventually, we'll talk about how scientists have to propagate or carry this air forward and state it with their final answer. So you want to minimize the air by not rounding till the very end if you can. So when I set up my formula, SR is going to divide to just 1. Sulfur is also going to reduce to 1 since it's divided by itself. And then the 2.1775 divided by 0.5444, in my calculator, because I haven't done any rounding, I've got 3.999816. So I can round that to 4. So I've got SR SO4 is my empirical formula. Formulas for a hydrate. I'm not going to spend a lot of time on this. Hydrates, basically, you find the formula very similar to how you do it for empirical formulas. A hydrate is an ionic or crystal structure, and remember, crystal structures are those alternating positive and negative ions, and there's space between those ions, so there's room for water molecules to be attracted and held in there. That's what the stuff in disposable diapers does. So when the salt is trapped in there, it's called a hydrated salt or salt-holding water. And the amount of water is called the water of crystallization, how much water the crystals hold. And you can easily get the salt dehydrated or get rid of the water by heating it, and then we call it anhydrous salt. I don't know why we don't just call it dehydrated salt, but it's called anhydrous. So to determine the formula of the hydrate, you have to subtract the mass of the hydrated and the anhydrous salts, and that'll tell you how much water you have. Convert that to the mass of water and the mass of your anhydrous salt to moles, and then compare the molar amounts. There will always be at least 1 mole of water or some whole number bigger than that. The smallest number of water molecules the ion can hold, the crystal can hold, is 1, but it could hold 7 or 12, it can hold a crazy amount. But that's the idea with hydrates. Percent composition, molecular formula. Percent composition is pretty easy because it's just a percent. So the percent composition by mass can be determined from the empirical formula. So on our previous try it, I gave you the percent composition. You thought of that as grams out of 100, and you came up with the empirical formula. Well, if you have the empirical formula, you can do the same thing. You can reverse that ratio and come up with the percent composition. The molecular formula of a compound represents all the atoms in the molecule. So not just the simplest ratio, but how many actual atoms of each element do you need to make that molecule. So the molecular formula has to be a whole number ratio of the empirical formula. You can't have 1.5 oxygen atoms. You can have 1 or you can have 2, but you can't have 1.5. So if you know the molar mass and you know the empirical formula, you can easily find the molecular formula. For example, so let's look at an example here of a compound called calomel. It's once used to treat syphilis. It has the empirical formula HgCl. Now, mercury isn't something we commonly treat anymore. That's why people with syphilis tend to go crazy. It wasn't the syphilis, it was the treatment. But anyway, it has a molar mass of 472.08. What's its molecular formula? Well, HgCl would only have a mass of the 200.59 for 1 mercury and 35.45 for 1 chlorine. If I add that up, that would only be a molar mass of 236.04. So if I take 472.08, it's obviously heavier. So how much heavier? Well, if I divide those, I see it's 2 times heavier. So I have to take the 2 times the whole formula, and I can assume the molecular formula is Hg2Cl2. So if the molar mass of celestine is found to be 183.7 grams per mole, what's its molecular formula? Well, remember, you found the empirical formula back in try it number 1. So if you find your empirical formula, it was SRSO4. So if I add up the molar mass for just that amount, I have 87.64 for the strontium, 3207 for the sulfur, and 64, 4 times 16 for the oxygen. I get a mass of 183.70. So that's letting me know that not only is that the empirical formula, but it's also the molecular formula. Okay, so back to combustion. At least one of those examples, it said it was found by combustion. So most compounds will burn or combine with oxygen under the right conditions. So if you have the data from combusting something and it tells you how much of each element you have, it told you how much strontium, how much sulfur from, we can assume they did some kind of spectral analysis, and then you can assume the remainder is oxygen, that's great. But sometimes combustion yields products that include compounds instead of just elements. Then we have to do a little more work. So here's my example to look at. If you had 0.5438 grams of a sample of a compound known to contain only carbon, hydrogen, and oxygen, and it's completely burned in oxygen, and the products were 1.0390 grams of CO2 and 0.6339 grams of H2O, what's the empirical formula? I guess I never actually put my question, but that's the question, is what's the empirical formula? Well, I wrote a skeletal equation for what we have here. We have some kind of CHO compound weighing 0.54388 grams. It's going to combine with an unknown amount of oxygen. Okay, so we're adding oxygen in, so at the end here, the oxygen on this side is going to be coming from 2 sources, so that makes things a little trickier. And we're going to end up with CO2 and H2O, and we know how much each one weighed. So we have the skeletal equation, and we have the amounts given to us in the problem. So how can we get there? Well, to get the moles of everything, I can first convert the products to moles, but that'll be for CO2 and H2O. But then I can use my molar ratios to figure out how many moles of carbon and hydrogen that actually represents. And then I can actually find out how much oxygen there is, because if I know how many grams of carbon and hydrogen I have, I can add those up and subtract them from my original compound, and whatever wasn't carbon and hydrogen has to be the oxygen. And then I can get my moles of oxygen. So after a little finagling, I will finally have all the pieces I need to do an empirical formula. So I'm going to go ahead and work through this. Feel free to pause and do any of this that you think you're up to on your own. So the first step said to go ahead and convert the products to moles. So I'm going to take the 1.0390 grams of CO2. Using my periodic table, I see that 1 mole of CO2 weighs 44.01 grams. So that's 0.02361 grams of CO2. Well, in moles, I'm sorry. Moles would be a big difference because that's what we want here. So that's my moles of CO2. And I can see I get 1 mole of carbon from 1 mole of CO2. So this is also 0.0236. That is my moles of carbon, which I'll come back to a bit later. If I do the same thing with the H2O, 0.6339 grams of H2O, 1 mole of H2O weighs 18.02 grams. So this is really 0.03534 moles of H2O. But now in this case, I get 2 moles of hydrogen from each mole of water. So when I double this, we're actually talking 0.07068 moles of hydrogen. So now to get my oxygen, I have to find out my 0.0236 moles of carbon times 12.01 grams per mole plus my 0.07068 moles of hydrogen times just 1.01, because now we're talking just hydrogen. We already took care of the H2. If I do that, I find out that those 2 products have a combined mass of, let me find my notes here, 0.3550 grams. So now if I go back to my original, this is how much carbon and hydrogen are in my products. So that's how much carbon and hydrogen had to come from my original unknown, because that's the only source of carbon and hydrogen. So now I can take my 0.5438, the original mass of the CHO, the unknown, minus the 0.3550 grams that we know is carbon and hydrogen. And when I subtract those, I get 0.1888 grams. That's got to be my oxygen. So how many moles of oxygen is that? Well, if I divide by 16 grams, I'm going to come up with 0.0118 moles of oxygen. So let me slide this down a little bit, see if I can keep my notes on here. So now I have carbon 0.0236, hydrogen 0.07068, and oxygen 0.0118. And if I divide each of these by my smallest amount, I should come up with my empirical formula. And when I do that, the C comes up to 2, very darn close. The H comes up to like 5.96, so I can round it to 6. And then the O, of course, would be just 1.